Okay, question 2a. A hollow hemispherical porcelain bowl shown in figure 2 has an inner radius of 5 centimeters and outer radius of 6 centimeters, initially at a room temperature of 25 degrees Celsius. So as for heat transfer problems, as you go through the question, as you read through the question, try to note down the relevant values, okay? So you note down the relevant values as symbolic form. So what do I mean? So okay, first, anything that you can change to SI units, please change it to SI units. So 0.05 meters is 0.06 meters. Then this, it says initially, okay? This is the key word. Initially, it is at the temperature of 25 degrees Celsius. So we know that this is T initial, okay? 25 degrees Celsius. The bowl is submerged in hot water, maintained at 90 degrees Celsius. So you see, it is surrounded by a fluid of a constant temperature. So fluid temperature refers to the ambient temperature. So actually this is T infinity of 90 degrees Celsius. Okay, so a fluid temperature refers to either liquids or gases, okay, a surrounding liquid or surrounding gas. The convective heat transfer coefficient is this. So this refers to your H. So H is equal to 10. How long does it take for the bowl to be heated to 60 degrees Celsius? Okay, so you know that this is a transient problem, right? Because they ask for how long. Transient problem means problem that changes with time. Okay, so in this case, a temperature, this is the temperature of the bowl that changes with time. Okay, and you know it involves time because they ask for how long. How long is they're asking for a duration? They're asking for how many seconds. Okay, so how long does it take for the bowl to reach 60 degrees Celsius? So what is this? The first part. Okay, let's take this as the first part of question 2a. So this is part 1. So part 1 is asking find find the time t such that the temperature at T is equal to 60 degrees Celsius. Okay, so they're asking for this. And when you know there's a transient problem, automatically you know that this must be a lump capacitance problem. Okay, so go back to my tutorial regarding lump capacitance if you want to know the basics. Okay, I run through the steps here. But for now, we're going to apply the steps directly. So you cannot apply the lump capacitance formula straight away. You must check whether lump capacitance is valid or not. So you must check it by calculating the Biot number. So Biot number is given by HLC over K. LC is calculated using the volume of the bowl divided by the surface area of the bowl. So let's calculate the volume and the area. So to get the volume, how do we examine this? Okay, this is a secondary school geometry problem. So for those who struggle with geometry, right, this is how I'm going to think of it. First, you start out with a large sphere of radius R2. Okay, this radius is R2. Okay, then what you do is you cut out a spherical hole inside. Okay, this radius is R1. Okay, is the inner radius. And then because this is a hemispherical means half a sphere. Okay, so what you need to do is you will cut it in half, right? So you cut it in half and you throw this away, right? And what you're left with is this shape here. So having that in mind, okay, what is the first step? The first step is I have a large sphere of radius R2. So you know the volume starts with 4 over 3 pi r cube, okay, r2 cube. Then what I do, I subtract away an inner sphere, okay? Subtracting away an inner sphere means I take minus 4 over 3 pi r1 cube, okay? But instead of this, I'm going to factorize this out, 4 over 3 pi, 4 over 3 pi. So when I factorize it out, it will leave something simpler. It will leave an expression like this, minus r1 cube, okay? So this volume is the volume of a sphere with a spherical shell, okay? Spherical shell, okay? But we only want half of it, right? Because it's a hemisphere. So what we do is we cut this in half. So we cut this in half, we throw this away, and we're left with the bottom. Okay, when we cut it in half, effectively, we're taking this, then we divide it by 2. Or in other words, you multiply it by half. Okay, you multiply it by half. So 4/3, yeah, pi 0.06 cube minus 0.05 cube times half. And at the end of the day, you should get 0.0000381. Okay, so this is the volume in meters cube. What about the area? The area, okay, how do we get the area? So let's examine this, okay? We're dealing with a hemisphere. A hemisphere is half a sphere, right? So you know that for a full sphere, the surface area is given by 4 pi r squared. Okay, 4 pi r squared. But if you want half of it, right? So if you want half of this, so that means you only want half of it, right? So you have to divide this by 2. Okay, you have to divide this by 2. So what you must do is times half. So that will give you this area, right? So let's examine how to get the surface area of this ball. First thing first is we want to calculate this surface area. So the bigger hemisphere. So to do that, you take 4 pi r2 squared multiplied by half. Next thing you want is you need to add the next set of area. So what's the next set of area that I want? I want the inner hemisphere. So the inner hemisphere, okay, is also the inside that face is also a hemisphere. So that means again I take a surface area of the sphere, so 4 pi r1 squared, then multiply by half because it's a hemisphere. Next, what else are you missing? We're missing this one, the rim. Okay, the rim of the bowl. The rim of the bowl. Now let's examine what's the rim of the bowl look like. So if I have a top view of what the bowl looks like, so I put my eye here and I look down on the bowl, the rim of the bowl looks like this. Okay, so it's a circular ring. This is called an annular circle. Yeah, annular circle. So to calculate this area, we must take the area of the bigger circle minus the area of the smaller circle, right? And that's easy enough. So that area will be given by pi r2 squared, so the area of the bigger circle, minus pi r1 squared, so the area of smaller circle. Okay, you substitute all the values, you punch this out in your calculator, you should get this. Okay, meter squared. So now we have the volume, we have the area, we are ready to calculate the characteristic length. So the characteristic length, you just take the volume divided by the area, so 0.0000381 divided by the surface area, so 0.04178. And you'll calculate out this area. Okay, so what you do is you substitute this characteristic length. So sub it back into the Biot number formula. Okay, 10 times this answer divided by the conductivity, and you should get 0.0608. Now examine this. We calculated that our Biot number is 0.0608. Ask yourself, is this less than 0.1? And the answer is yes, this is less than 0.1. Meaning to say it passes the test. So that means lumped capacitance is applicable. Okay, so the formulas that we've created for lump capacitance is applicable, and let's go ahead and find it. So we want to find time, right? Because we're asked for how long it takes. Remember, our question is find t such that, let's go back up to the question. This is our question. Find t such that the temperature is 60 degrees Celsius. Okay. So the formula for time is given as this. Okay, where theta I is given by Ti minus T infinity, and theta T is actually temperature of T minus T infinity. Actually, the theta here at the bottom is a function of time, right? It's actually there's an invisible T here. It's a function of time because this is a function of time. Okay. So Let's sub in the values. But first, let us check. What is this volume over area? We know that this is the characteristic length, right? This is the characteristic length. So actually, RVCP over HA, this term, we can replace it with RLCCP over H, okay? RLCCP over H, okay? So I don't need to plug in the volume of the area separately. I can just replace this term with the characteristic length. So they give me the density as 2300. We calculated the characteristic length earlier. Heat capacity, convective coefficient, and then you replace theta with these two values. Initially at 25 degrees Celsius, water is 90 degrees. We want to end at 60 degrees Celsius. Okay, calculate this and you get 1760.24 seconds. Okay, if you want this to be a little more elegant, you can divide this by 60 seconds to convert it into minutes, and then you'll get 29.3 minutes. Okay, so a reasonable answer. Okay, the next part of the question says this. So if the bowl is then taken out of the hot water to dry in ambient air with a convective coefficient of 25 degrees Celsius now, so the H has already changed. How long will it take to cool to 35 degrees Celsius? Okay, how long will it take for the bowl to cool down to 35 degrees Celsius? So you need to understand what's the problem now. Okay, the problem is this. So remember at first, we have this porcelain bowl at 25 degrees Celsius. Okay, so at first, this bowl was at 25 degrees Celsius, right? And then we have a big tank of water whose temperature is maintained at 90 degrees Celsius. So what we do is we dump this bowl in. Okay, we dump this bowl in, and then at first it is 25 degrees Celsius. Then the temperature rises up until it reaches 60 degrees Celsius. Okay, so let me draw a graph of temperature against time. So this is temperature, this is time. So they're asking us, okay, at first we have this is at 25 degrees Celsius. Then the temperature rises like this, okay, until it reaches 60 degrees Celsius. So at first we already calculated this time. Okay, we already calculated this time. And now after this time, it is immediately taken out of the tank of water. So now we take out the tank of water back into the temperature, a room temperature of 25 degrees Celsius. And then now it has an initial temperature of 60 degrees Celsius, right? So now our Ti is 60 degrees Celsius. Okay, so now this will cool down, cool down, cool down, cool down. And then we're asking for, let me draw this graph better. So we're asking for the time when this becomes 35 degrees Celsius. Okay, so we're asking for this time now. Okay, so time 2. So how long is this duration? So you check. So this is part 2a part 1, and then now we are looking for 2a part 2. Okay, so how long does it take for the bowl to reach from 60 degrees Celsius to 35 degrees Celsius? So you know that now this is the initial temperature, right? So Ti is now 60 degrees Celsius. Then this is now Tt. So T of T is 35 degrees Celsius. Okay, and now H has updated to 25 degrees Celsius. Then the ambient temperature also, sorry, this is 25 units. And then the ambient temperature has turned into 25 degrees Celsius. Okay, so take note of these value updates. Okay, so we still need to check for the Biot number. Don't forget, we need to check for the Biot number. Why do we need to check for the Biot number? Because the H has changed. Remember what's the formula for Biot number? Biot number is HLC over K. Okay, LC has not changed. Why? Because the volume, okay, LC depends on volume and area. The volume, obviously the bowl, right, did not shrink or enlarge. So the volume remains the same, the area remains the same, therefore the characteristic length remains constant. Okay, so LC did not change. K did not change because the material did not change. Okay, but the thing is H has changed, right? The question has explicitly told us that H has changed into 25. So we must recalculate the new Biot number. Okay, you must use the Biot number to check whether the lung capacitance is applicable. Now take a look at this. Your Biot number is now 0.015, sorry, 0.05, sorry, 0.152. Okay, ask yourself, is this less than 0.1? And the answer is no. Okay, it is not less than 0.1. It is in fact greater than 0.1. Okay, but the thing is, you see, this is 0.15. This is 0.1. We are so close to becoming 0.1 actually. So this is the comment that I'm going to make. Okay, so you must explicitly write this down as part of your solution. So the comment that I'm going to make is this is slightly above the threshold of acceptability. Okay, so that means this is slightly okay. The solution. Okay, so solution will slightly deviate from reality. So we need to make an assumption, and our assumption is that assume lumped capacitance is applicable. Yeah. Okay. So slightly above the threshold of acceptability. Now, what do I mean by threshold of acceptability? I'm referring to this. This is the threshold of acceptability. Threshold means the condition, the criteria, and the criteria uh is that Biot number should be less than 0.1. But no, now we have Biot number is equal to 0.15, which is slightly above it. So that's why I said that it is slightly above the threshold of acceptability. So solution will deviate slightly from reality. Okay, so since it's just a bit over the Biot number that we want, it's going to be a bit different from reality. That's why I say solution will slightly deviate from reality. But we must go on. Otherwise, we have no solution. So we must assume that lung capacitance is still applicable. Okay. Now you continue on with your life. So remember, we want to find T such that T of T is equal to 35 degrees Celsius. Right? So you use the time formula. Okay. Recall that this theta I refers to Ti minus T infinity, and theta refers to T of T minus T infinity. Then remember, V over A is the characteristic length, then rho is still the same. So this is the characteristic length, specific heat capacity. And then remember, H has already changed to 25 now. So here will be 60 minus 30, 25 divided by 35 minus 25. Okay. So if you calculate this, your time will be 1140.81 seconds. And if you want to divide this by 60 seconds, it will become 19.0 minutes. Okay, so that's the duration, and this is a lung capacitance problem. So see you in the next video.